Let's do a first simple example of bending stress on beams. The first thing which we want to do in these kind of scenarios is to do once again the free body diagram and calculate the equilibrium equations learned from the statics. So first thing, I'm gonna draw the free body diagram here like this. On the left hand side we have FAY, we have FAX. On the right hand side we have only FBY. And here, half a meter from left hand side, we have external force of 10 kilonewtons. Sum of all forces in horizontal direction has to be 0. We don't have any external horizontal forces, which means that if AX equals to 0, like so, sum of vertical forces has to be 0. We have FAY minus 10 kilonewtons. 10 kilonewtons, the external load is downwards, which is according to our sign convention, it is negative, and then we add there FBY, and this has to be 0. And finally, the third equilibrium equation is the sum of all moments has to be 0. I will be calculating this around the point A. So we have to a negative direction we have 0. We have 0.5 meters times 10 kilonewtons plus total length is 2 meters. 2 meters times FBY, and this has to be 0. Well, let's number these equations as we always do. This is number 1, this is number 2, and this is finally number 3. And from equation 3 we can simply solve that the FBY equals to 0.5 times 10. Let's add the units, meters, kilonewtons, divided by 2 meters. Meters get subtracted away, and we see that the FBY has to be 2.5 kilonewtons. And then finally, from equation number 2, we can easily solve that FAY equals 10 kilonewtons minus FBY, which was 2.5, which means that FAY has to be 7.5. Like so. Well, next thing that we have to do in this kind of examples, calculations, is that we must draw the internal bending moment diagram. In a simple example like this one, we would not need necessarily the shear force diagram, but in more complicated examples with more complicated external loads, we are going to be needing also the shear force diagram, and therefore I always like to draw it even though it is not necessarily mandatory. So first let me draw here a new free body diagram with the calculated forces in it. So here we have this, and then in here we have 10 kilonewtons. In here FA was 7.5 kilonewtons in here, and then finally in this here end here we have 2.5 kilonewtons, like so. Now drawing the shear force diagram. So first, when we have external force pointing upwards, it means that we are going to be having shear force, internal shear force downwards, which is our positive direction according to our sign convention. So at the beginning, we're gonna jump to our internal shear force is going to be jumping to value of 7.5. It will remain on that level until we reach the next point. This is positive here. At the next point, we have 10 kilonewtons pointing downwards, which means that the internal shear force is going to be jumping to the other direction. In here we had 7.5. Now when we introduce the external load of 10 kilonewtons, it means that it will jump to value of 2.5 to other direction, like so, and it will remain on that level until we reach the end of the profile, because there are no other loads in here, and then finally at the end it will go to 0, and this is now negative, like so. Let's highlight this area. Okay, after that we can easily draw the bending load diagram. So, bending moment diagram. So, let's draw it in here. So at the beginning we have a hinge type support, which means that we don't have any bending moment at the beginning of the profile. Then when we start from left hand side, we start going to right, we know that our external load 7.5, or the support reaction 7.5 kilonewtons is causing bending moment. Based on our sign convention, we know that when we have positive load, so positive force direction is upwards, it means that the bending moment caused by that is also positive, so we draw it in this direction, and the bending moment caused by external load like that is always linear, like so, and the value at this point will be MB. Let's mark it with number 1. MB1 equals to 7.5 kilonewtons multiplied by the distance, which was 0.5 meters, and the value will be 3.75 kilonewton meters. And then we have this external force here, which starts to reduce because it's pointing the other direction, and we know that is the only force we have, and at the end we must land to 0. It means that when we start drawing the line, we will end up to 0, like so, and the bending moment inside the material is positive, like that. And now we see that the maximum value of bending moment in our structure is 3.75 kilonewton meters. Well, now when we want to calculate the stress in the profile, we are going to be needing the second moment of inertia of the profile. In this example, the profile was simple, a rectangular profile like so. The height of the profile was 100 and the width was 50, like that. So this is the height, this is the width. So the second moment of inertia, around the y-axis for this profile is 50 times 100 power to 3 divided by 12. And if we want to calculate the section modulus, the section modulus Wy will be 50, which is the width, multiplied by height power to 2 divided by 6. And now with the equation for the stress, which is sigma equals to bending moment divided by section modulus, we can calculate the stress for this profile, which will be sigma equals 3.75 kilonewton meters, which was the stress which we just calculated, or the bending moment which we just calculated, divided by the section modulus, which is 50 millimeters times 100 millimeters power to 2 divided by 6, and the value for this one will be 45 megapascals. Like that. In this task, we were also asked to calculate the bending stress if the beam was rotated 90 degrees, like so. So the height would be 50 and width would be 100. Well, we can easily calculate this with the same equation. We just have to recalculate the section modulus. So the sigma is 3.75 kilonewton meters divided by 100 millimeters times 50 power to 2 millimeters power to 2 divided by 6, and the result for the stress will be in this scenario 90 megapascals.